Hello, I'm Johann Graf Lambsdorff from the University of Passau, and I would like to talk today about the new Keynesian Phillips curve, which is a very particular novel type of Phillips curve. In a related video, I showed you how to infer from a classEx game, how to infer the traditional Phillips curve. Now the new Keynesian Phillips curve is a little different, and in particular it is a relationship again between inflation and the output gap, but this time we have inflation pi in the current round or in the current year t as a function again of inflation. But this time it's not the lagged inflation, it's future inflation. So in round or year t plus 1 plus some parameter gamma times the output gap, which you hopefully know already from the other video. Now, in order to derive this type of a forward-looking Phillips curve, you should start by playing a classEx game. And here I have the classEx game. Find a lecturer who plays that with you, or if you join my own lectures, we will run the game there. Now, I must excuse because this is a pretty dense description here, and I will simply read out the instructions for you in order to follow this. You will play 5 repetitions. So by help of some repetitions, we make sure that as a student you can learn how to play, that you have a chance to come close to playing this optimally. And you start with 13,500 euro cents, so that's 135 euros on your account. In each repetition, you must try to get your price as close as possible to a target value over 12 rounds. You cannot, by the way, you see the rounds down here, so from 1 to 12. You cannot set your prices directly, you can only submit price proposals. Chance determines whether your price proposal is realized. With probability 1/3, your price proposal is realized. With probability of 2/3, your price proposal is not realized, and the price of the previous round remains in place. So think, for example, that your sales agent is living at a distance, and you're sending an email updating your sales agent about the new price. However, this email reaches the sales agent only with a probability 1/3. And otherwise, the sales agent will continue with the old price. In each round of repetition, the squared deviation between your price and the target value will be deducted from your account. So price minus target value squared. That's the whole thing. One participant will be drawn randomly and receive the payoff from their account. So there is a real incentive to play and to optimize. Now, what you see here refers to what we can see as a type of a rigidity. As a producer, you cannot directly determine your price. There are some rigidities, and in this case, that your price proposal is simply not realized. In other cases, there might be costs to adjusting the price, menu costs, writing new menus, and people may sometimes prefer not to adjust the price because the menu costs are too high. So there are lots of reasons why there might be rigidities, and we have a very particular one, and in essence what we have here is the idea advanced by Guillermo Calvo in 1973 where he developed this type of a model to infer optimal pricing behavior in light of the idea that sometimes you just cannot change the price. Okay, now what we get here at first is, well, let's take a rather general form. Here in the game, the price, your price proposal is implemented with probability 1/3. So let's use the general parameter alpha. And in our case, this is just 1/3. And when you have this, basically, you can determine the price in round t. And the price in round t will depend on your proposal, and I call this the xt. So you submitted a proposal. Now you see here how the target values are determined. You see this in this graph. In the beginning, your target value is 100, and you might have some deviation, but basically you also start with a price of 100. So in the beginning, the price is identical to the target value. However, starting in round 7, the target value suddenly drops to a value of 60. Okay, now when you submit a price proposal, then this xt, then this is implemented only with a probability alpha. And with the probability 1 minus alpha, it is not implemented, and instead the old price remains valid. So then we have pt minus 1. So you see here at first some sluggishness, some inertia. And when you look at this inertia, you might think that the resulting Phillips curve should also have some inertia. The surprising thing about the Phillips curve, the new Keynesian Phillips curve, is that it is completely forward-looking. So why is that so? Well, you can guess already by looking at the classEx game, because your challenge is that in round 7 you will for sure implement a price proposal of 60, because anything else doesn't make any sense. You want your price to go down. However, you might already in round 6 observe that a lower price proposal makes sense, because if that is implemented, you will certainly then suffer from the loss in round 6, because then you have the deviation to the target value. But on the other hand, you have the chance that in round 7 until 12, you have a minor deviation from the target value in case your price proposals that you submit then are not realized. So that supplies you with an idea that should be somehow intuitive. We have a quadratic loss function, and this quadratic loss function implies that small deviations are okay, but large deviations hit you in a quadratic style. So what is surely not a good idea is to set a price proposal in round 6 of 100, because in that case you might avoid losses until round 6. But if your price proposal of 60 in round 7 is not realized, then you suffer a really huge loss. So you should smooth somehow your price development. You should smoothly sort of approach the 60. Now, how can we infer the optimum path of price proposals? Well, this is the task for today, to find this optimum. Let us assume for a moment that in round t, xt is realized. And we take this as a starting point for finding the optimum value, and we can do so because if your price proposal is not realized, then it was completely irrelevant. So let us find the optimum level only if it is relevant at all. So we assume xt is realized. Now, if xt is realized, then it might not be updated for quite some time. So it will not be updated, until t plus j. So for j rounds, it may not be updated. And how high is the probability that this happens? Well, the probability if not updated until t plus j is equal to 1 minus alpha to the power of j. Let me illustrate that. So, just very, very quick. We start with a probability of 1, and here with round t plus 1, t plus 2, t plus 3. Okay, in round 1 we said, well, it's realized. So then we're here. In round t plus 1, well, with probability alpha, which in our case is 1/3, a new price proposal will be realized such that the old one is updated. So it is not updated with probability 2/3. Okay? In t plus 2, again, there is a chance of 1/3 that the old price proposal is updated. So 2/3 squared, that's about 44%. That's somewhere here. With this probability, again, it's updated. In t plus 3, it's 2/3 to the power of 3. So then we're here. So it is this type of a, well, exponential function that approaches 0 but never completely reaches 0. Okay, now when choosing xt, the task is to compare two costs, two disadvantages. The one is, well, if you have on the one hand the certain costs in the current round, if it is implemented, the certain cost, for example, in round 6, going down with the price proposal that is implemented, implies that there is an immediate cost. And there are further costs starting in round 7, when the price target is down, serve another cost that runs into the different direction. So how can we bring all this together? What we're looking for is a cost minimum. And what we want to minimize is the sum of all future squared deviations. This sum of all future squared deviations, that is well, our task is minimize by choice of xt the sum from, starting from, well, my running index, that's the j equals 0, and until infinity. Well, basically in the game it only runs until around 12. But let's simplify, because as you may know, the using the infinity here allows for some nice applications for infinite rows of numbers. Okay, so we're looking for this row of numbers, and what we have here is the squares deviation between our chosen price proposal in round t minus the target value z of t plus j, because now the j runs from 0 to infinity, and it certainly will take different numbers across time. And now we take the square of this. However, this price proposal might be updated. So the game is over, sort of, because then we have a new choice, a new chosen price proposal, when the old one has been updated. So this is valid only for 1 minus alpha to the power of j, as we had it here. Okay, now this is what we want to minimize. And since we want to minimize that, well, quite surely we take the first derivative of that. And we know the first derivative in a cost minimum must be equal to 0. So what's the first derivative of this? Well, that is this whole sum from 0 to infinity, and this exponential function, that's all the same. And now we just take the interior derivative. And the interior derivative of this is, well, 2x t minus 2z t plus j. I hope you can see this. We basically only bring the exponent in front and multiply, reduce the exponent by 1, and then this is what we get. So this must be equal to 0. Okay. Now, this can be simplified easily. First thing to see is this 2. We don't need that. We just divide by 2 on both sides, so that's gone. What else? Now, the xt basically is a constant. And we can rewrite the whole sum by seeing that we have the sum from 0 to infinity times 1 minus alpha j times the xt. And now I split up the whole sum and I subtract the second part from 0 to infinity, 1 minus alpha j to the power of j times z plus t plus j. That must be equal to 0. It's easier to say, well, this must be equal to this. Okay, now the xt is a constant. And since it is a constant, we can derive a very simple formula. We can apply that. 1 minus alpha to the power of j running from 0 to infinity, that is just 1 over alpha. So this is 1 over alpha times xt. Okay, if you don't know this formula, just look it up. It's a standard standard solution for this infinite row of numbers for an exponential function. Okay, how about this side? That is a little more tricky. So what can we do about it? Well, let me start the other way around. Now we have a formula for xt here. That xt, so if we multiply with the alpha, we get this equal to this alpha times this sum. What do we know for xt plus 1? Well, using this formula, it must then be equal to alpha times largely, well, this sum running from j equal to 0 to infinity times 1 minus alpha to the power of j times z. And now I must think about that. I have here t plus 1. And therefore, this t must be expanded by 1. Because for my xt, I don't want the regular target values, but rather those that are advanced one round into the future. Now, okay. I can rewrite this here. I can rewrite this because I prefer not to have the 1 in here. Rather, I would like to shift my running index 1 round to the future. So I don't start with a 0, I start with a 1. But when I do this, I must subtract. Each time that I refer to the running index, I must subtract the 1 again. So I subtract the 1 here, and I subtract the 1 here. Okay? Now what you see here is already very close to the solution, because what do we have? The xt is equal to alpha times this sum from j equal to 0 to infinity. And let me just repeat it. 1 minus alpha to the power of j times z plus t plus j. However, now I split into 2 parts this sum. The first part is for j equal to 0. Now when j is equal to 0, then I have 1 minus alpha to the power of 0, which is 1, and here I have only zt, which is then alpha zt. Okay? And the next part of that is the sum of j starting with a 1 to infinity times all this. Right? But then you see this is very close to what we have above. It's almost identical. The alpha, starting with a 1, starting with a 1. 1 minus alpha to the power of j, 1 minus alpha to the power of j, but here's the 1 minus 1. This is the only difference between the two. If we bring this, so if we consider this here, we would have to multiply the xt by 1 minus alpha. I'm sorry, here. Let me do it better. If we recognize this here, we could simply take out the minus 1 here and divide the whole term by 1 minus alpha here. Or multiply by 1 minus alpha, and then we have 1 minus alpha times x t plus 1. So what we get here is alpha zt plus 1 minus alpha xt plus 1. Now that is a very brief solution, and it allows us to understand how one should determine the optimum. So I hope this is still visible. Let me just have a look. Oh, it's a little outside, so I'm moving a little upward. Should be visible now. Is it? Yeah, that's better. Okay, so we're having the 100 here and the 60 here. And you know, in round 7 and 8 and so on, you will for sure set a price proposal equal to 60, because anything else would just be a waste. The question is, what will you do in round 6? And here is the answer. Determine round 6 by looking forward. You know in round 7 you will pick the 60. So take 2/3 of the 60 and take 1/3 of the current target, the 100. The 100 is up here. The 60 is down here. So take 1/3 of the old target and 2/3 of the one down here. So one should be around 73. Right? Moving downward 2/3. And round 5. What should you do? Well, you should know that in round 6 you're going to take the 73. Now take 2/3 of the 73 and 1/3 of the 100. So again, from the 73 move 2/3 down and 1/3 remaining away from the 73. And that is a value of 82, I think. And in round 4, you should do the same. So overall, you get this type of an optimal path of your price proposals. Now that should help you understand why rigidities, with fully rational and sort of forecasting, perfectly anticipating players, induce them to be purely forward-looking. And what you see here is whatever you did in the past, it doesn't matter. History plays no role in the new Keynesian Phillips curve. Now, we still don't have the new Keynesian Phillips curve. So what can we do? How can we infer the new Keynesian Phillips curve from this very parsimonious function? Here I tell you how it goes. So my Lightboard is a little packed already. So let me... Okay, give it a try. So I have the xt should be equal to 1 minus alpha times xt plus 1 plus alpha zt. Okay? So this is what we have. Now I simply expand this by subtracting the current price level, PT here. And in order to have this adequate, I am subtracting the current price level here. I hope that is still all visible. Yes. Now, I've subtracted that here, but I would like to link this price level to the target. So I put this in brackets, but then I have only subtracted alpha times PT. So what I have to do is subtract the rest as well. So I have plus 1 minus alpha minus PT here. Okay? And next trick, I am adding here also the future price level, PT plus 1. And since I have added this here, I must subtract it up here. You see, it's always multiplied by 1 minus alpha. So I hope you're with me that, well, the simple magic was rather trivial, so I did not do lots of horrible things. We're still faced with the following problem. This is a function that refers to prices, and prices are observable. We know them. We have macroeconomic data on prices. However, here we have a function, and here as well, related to price proposals. This is what is mostly only in people's mind. They would like to have a certain particular price level, but we don't know about that. It's not observable. So we must somehow transform this equation to something that is observable. So this PT plus 1 minus PT, that is observable. So that's nice. But we must get rid of these x's here. And we can do this by using this formula. The very simple one. When we use this, we simply, so I insert this here, small calculation here. So what we do is we have the PT being equal to alpha times xt. Now what was my trick? Oh yeah. This 1 minus alpha times PT minus 1, I bring this to the left-hand side. So I am, and I need a little more space in front of this. So this is just PT here. So I am now subtracting the PT minus 1. But that was multiplied by 1 minus alpha. But since now I have here only PT minus 1 times 1 minus alpha, but previously it was without the minus alpha, for that reason I now have to subtract the minus alpha on this side as well, which I do this way. Okay? Well, basically, that is the whole magic. Because if I divide by alpha, we now see that xt minus pt is equal to something that is expressed purely in prices. It's equal to 1 minus alpha over alpha times pt minus 1. And I insert this up here to see then that we get 1 minus alpha over alpha times pt minus 1 and that is equal to 1 minus alpha. And now look at this. This is basically the same expression as here, shifted one round to the future. So this is, we can then insert for this by also shifting this one round to the future. And here we have the 1 minus alpha from here. The 1 minus alpha from here makes it 1 minus alpha squared over alpha times pt minus pt plus 1. This is shifted one round to the future, minus pt. Okay? And then I continue with the rest of this equation, plus 1 minus alpha times pt plus 1 minus pt plus alpha times zt minus pt. Okay, that still looks quite complicated, but in fact it really isn't. Because I now simply multiply by alpha over 1 minus alpha on both sides to see that this left-hand side simply collapses to pt minus 1, which must now be equal to, well, this is only 1 minus alpha times pt plus 1 minus pt. And this now is, well, I divide by 1 minus alpha and multiply by alpha. So this is alpha times pt plus 1 minus pt. But if this is alpha and we have 1 minus alpha here, I can simply take away the minus alpha here and this collapses to unity. So I have only this left over. Plus then the final term alpha times alpha, that's alpha squared, over 1 minus alpha times zt minus pt. And basically that's the whole story. We would still need some adjustments here, like for example dividing on both sides by pt, more or less. Then you will see that this is current inflation. This here becomes future inflation. Let me put this here. This here becomes future inflation. And this here, well, think of it the following style. The ZT is the target price, and the target price can be interpreted as the one price that brings demand in line with potential production. That should somehow be reasonable. When your price is at the target level, your production is somehow in balance. In balance, well, with what? Well, with potential production. So, when your current price deviates from the target value, it means that your demand is not corresponding to potential production, and that's the output gap. So overall, we can infer, for example, for round 7. When you go to round 7, you will you have a price target of 60, but your price on average will be above, because you will have set price proposals that were above 60 previously, and on average your price proposal of 60 in the 7th round will not be realized, at least not always. So on average, you will have a price that is higher. So you have the 60 here and something higher here, which means the whole term is negative. And that corresponds to a negative output gap. You will have a recession. Now, when you have a recession, it means your inflation is pressed downward. And this is exactly our Phillips curve that we know. A recession pushes downward the current inflation rate. Now, the novelty about this particular type of New Keynesian Phillips curve is here the influence of future inflation. Subjects are assumed to disregard history. They only look to the future. And for example, when you look at round 6, you will find something quite unusual. The target price is still very high, so the Z is 100. But it was optimal to lower your price already such that PT is lower, such that the whole term is positive. And that means there will be a boom. Subjects will respond to the anticipation of a future drop in the target value of sort of future deflation by having a temporary boom. Now, to be realistic with you, at first, I don't really believe that this type of a boom in advance of the shock is what we will be able to see in reality. It's very hard to test because macroeconomic time theories always suffer from identification problems. And that's the reason to bring such types of dynamics to the lab. Now, what do we see in the lab when people play this game? Well, basically, we repeatedly see underadjustment. There is a sense of going down a little, but most often subjects are way above the optimum. Somewhere, maybe this type of an adjustment. And that tells us that some anticipation does take place. And it takes place here because the game was substantially easier than reality. Because in reality, one does not observe such clear signals. In round 7, the price target is going to drop to 60. Rather, data will be much less certain. And this uncertainty is also widely discussed in the literature. From a Keynesian perspective, one would infer that people pay less attention to uncertain future values. Now here, that was an ideal test of how far people smooth this price path, perfectly knowing the future shock. And even here, they would tend to underreact. And that allows us to infer that this quite parsimonious New Keynesian Phillips curve is one of mathematical beauty, but personally, I would place much more value on the traditional type of New Keynesian, of the not New Keynesian, but of the traditional Phillips curve. Thank you for your attention.